Chapter 4, slides 19 through 27. In this part of the chapter, we're now going to be looking at the conformational analysis of alkanes. And we're going to show you a few different ways to represent conformations of different molecules. Now, the first thing to remember is that we're going to be focusing on alkanes. So we're going to be looking at the way that a carbon-carbon single bond or sigma bond can rotate. Remember, sigma bonds are head-on overlaps of their orbitals, and we can represent this using our hands or our fingers. And if we do that, we overlap those orbitals, and if you only have one bond, a sigma bond, you can rotate it and twist, right? And it's fine. Conformational analysis is a fancy term for molecules rotating and bending and basically just rotating around those sigma bonds. This is no different than you or I. We ourselves have different conformations, right? I could be standing up. I could then bend at the hips and sit down into a chair. One of these conformations is lower energy. I know which one is lower energy for me. It's certainly sitting in a chair. Molecules are no different. They can bend and twist into different conformations, and these conformations, some of which have lower energy than other conformations. Still, we're talking about the same molecule. We're not breaking bonds or making bonds. We're simply twisting and bending the bonds that are there. And we can only do that, twist, that is, around bonds that are sigma or overlapping orbitals directly. So conformational analysis is best done when you can draw the same molecule in different ways to show those different conformations, just like you can show someone sitting up or sitting down in a chair. And there was some phenomena that led to this discovery that certain conformations were in fact lower in energy than others. At first, it was presumed that, these bonds are just rotating willy-nilly all over the place and they could be in any conformation at any time. But in 1937, the entropy of ethane, which is arguably one of the more simplest, right, carbon-carbon single bond molecules, where you can twist along that single bond, it was found to have somewhat lower than calculated entropy. So what that suggests is that the rotation of one of the groups, one of the carbon CH3s, has a better conformation or lower energy conformation than another, that there was a difference. So this reduced entropy was taken as an indication that the CH3 group has a reduced freedom of rotation. And what this means is that although you can rotate, it's going to do so to maximize being in its lower energy conformation more often than the higher energy one. So how do we know which one is high energy and low energy? Well, we can take a look at the things called eclipsing strain, or it's also called torsional strain. And if you think about that, this is going to be when you've aligned, like an eclipse, all of the bonds of to the hydrogens with the other carbons' bonds to hydrogens. And this might be difficult to see. The way that we have, or that we've been drawing molecules has been using bond line structure, and we draw this zigzag for the carbon backbone, right? It's a very quick and easy way to make a long chain of carbons. The other nice thing about using this zigzag is it naturally places, if you're putting the wedges and the hashes in the right trajectory, it naturally places everything in the best conformation. We're going to find that out later, but if you are looking at down any two carbons on this molecule, all of the bonds will be oriented around one another as far apart as possible. So what's wonderful about that quick bond line structure zigzag is you're already putting it in a conformation that is favorable. And there's a couple other ways to look at it. And one of the new projections or conformations we're going to view this molecule, I have this eye looking down, we'll call it carbon 1 and carbon 2. So carbon 1 is this black carbon. Carbon 2 will look with a see-through circle. So carbon 1 is in front. So if I place myself, right now, I guess when I'm looking at the molecule with the red and the blue, if I look at it from here, it's like looking at the side of a barn. I want to basically come around the molecule so that carbon 1 is right in front of carbon 2. So I can't even see carbon 2. So you'll notice from this trajectory, this is a Newman projection. And what I've done is I've just redrawn this same molecule, but from the front, looking down so that carbon 1 and carbon 2 are overlapping, and basically carbon 2 is right behind. So that means that the hydrogens in the front, I can see those 3 hydrogens are right in front of me, and the hydrogens in the back are on carbon 2, but I can't see that carbon, but you can see the hydrogens poking out. I have a few different ways using Newman projection to rotate around this bond, and you can see that rotating, if I keep the hydrogens in the blue in the back the same, and I just rotate the bond, I can spin this like a Ferris wheel and move them so that the hydrogens are now almost on top of each other, because again, there's free rotation around this sigma bond. So we're going to use these Newman projections to talk about the energies of eclipsing or torsional strain and steric hindrance. Here are different models of showing this is all the same molecule. This is all ethane. But we have different representations, in different conformations for ethane. We can use the ball and stick representations, computer models. I can show you the sawhorse representation. That's using, again, wedges and hashes. But if you'll notice, all of the bonds are eclipsed to one another. So if you'll notice this sawhorse representation right here, you can see all of the bonds are aligned with one another. The 2 hydrogens are coming towards you, the 2 hydrogens in the back, the other 2 sticking straight up. It's almost like they're mirror images. There was a mirror right down the middle of the molecule, and these 2 are looking at each other. Another sawhorse representation, but of staggered, meaning that the hydrogens are all out of each other's way, is shown in this middle figure. On the right are the Newman projections, and these are when you're looking down the barrel of the 2 carbons so that the 2 carbons are overlapping one another. And as you twist the bond, you can see I think it's much easier to see staggered. So here's staggered, and here is eclipsed down at the bottom here. Now, still talking about ethane, what you'll notice is that staggered conformations, they're all at the bottom here. As you move, and all I'm doing is I'm showing they're all hydrogens around the carbons, but I'm highlighting 2 hydrogens so you can kind of pay attention to the rotation. So the 2 of the hydrogens, one on the carbon 1 and one in the back on carbon 2, have been highlighted to be red. And as we move from staggered in energy, because again, this is energy, to eclipsed, we notice a bump in energy, right? I've only turned 60 degrees, and then I turn another 60 degrees and I'm back to a staggered conformation, lower in energy. Back to an eclipsed energy, higher energy. Back to a staggered. Back to an eclipsed. Back to the staggered, the original staggered I'd started with. So I'm changing the dihedral angle 30 degrees and it's alternating between staggered, eclipse, but all the atoms are the same. They're all hydrogens. So I get equal up and downs. There's a difference of 12 kilojoules per mole between the eclipsed and the staggered. That's pretty big. So the difference in energy between these two conformations, right? This would be, again, like a human standing in one conformation or sitting in another, different energies. And we can see that the staggered conformation has all of those bonds away from one another. Let's go back and look at that again. See the bonds? Let's just take a look at one bond, right? And every bond, which again is comprised of electrons, those orbitals are as far apart as possible. But when the bonds are eclipsed, they're kind of in each other's space. And so once you have those orbitals eclipsing, they're closer to each other. So and electrons repel, so it's higher in energy. So this is why it's called eclipsing strain or torsional strain. It's not about the substituents off of the carbon. It's about the alignment of those bonds, because the bonds are electron clouds. And so when you align the bonds, the orbitals with the electrons in them are closer to each other, and that's a higher energy. So it's calculated to be about 12 kilojoules per mole because for each alignment of the bond is about 4 kilojoules per mole. That means that at room temperature, 99% of this ethane molecule prefers to be in the staggered conformation. So you have a good idea of predicting at any snapshot of the ethane molecule how it's probably oriented. What is the sitting conformation for ethane? Okay, so now let's take it up a notch. Let's draw a Newman projection for propane. Okay, well here's propane. I want to now maybe look down the carbon-carbon bond, right? But don't you notice that there's a methyl off of carbon 1? Carbon 2 in the back has all hydrogens. Hydrogen, hydrogen, hydrogen. The carbon in the front has 2 assumed hydrogens, so I'll make those hashes and wedges. So if I'm looking down the barrel of the carbon-carbon bond, you can see that there's a methyl and 2 hydrogens in the front. And in the back, there's a hydrogen and 2 hydrogens down below. So that's a Newman projection. This is the Newman projection. It's you draw a circle and then you can see the ones connected in the front. You can't see the carbon behind, but you draw the 3 bonds off of that back carbon. Okay? It's like this is like the side of a barn. And then a Newman projection is like looking at the barn from the front doors. Right? So if I had like a barn, looking at the barn from this angle is the side of the barn. You can see the whole thing through its length, but looking at the barn from this angle, right? The projection of the barn from this angle is the Newman projection. The Newman projection, it's like you can't see the length of the barn. It's all like hidden behind, but you can see the front of it. So let's take a look at the torsional strain for propane. So I've kicked it up a notch. I added a methyl group. Okay, so that's highlighted in red, that methyl group. And what you'll notice is that there is a low energy for all the staggareds again, and an equal high energy for all of the eclipsing ones. So whenever all of the bonds are eclipsed, you can see that there is a torsional strain, and that is 14 kilojoules per mole. So there is a difference by 2 kilojoules between ethane, you can see the 12 kilojoules per mole, and adding that methyl group gives you a torsional strain of 14 kilojoules per mole. So there's something else going on here. What is that? Well, we calculated an extra 2 kilojoules per mole. So whenever we saw the methyl eclipsing one of the bonds with the hydrogen, that's an extra 2 kilojoules per mole than the normal 4. And again, these numbers are given to you. They're calculated through experiment. They're not to be derived by you. So do not expect to suddenly know these numbers, why and how. It's all calculated through experimental. So what you notice, though, is there's this extra strain, right, when you start increasing the size of the group. What does this do to? Well, we can better understand that if we increase the complexity of our molecule again. Let's look at butane. And let's look at the C2 to C3 carbon. So 1, 2, 3, 4. That's butane. And I want to look down the C2, C3 bond. So there's my eyeball. And I'm looking down that bond. So that means that I've got a wedged hydrogen and a back hydrogen, and a wedged hydrogen and a back hydrogen. So when I draw my zigzag and I put it in that conformation, I can now look, this is the side of the barn view, right? I now want to do my Newman projection, whereby carbon 1 is in the front, or actually in this case it's carbon 2. Carbon 3 is in the back. And from this side, I can see left and right hydrogens up at the top and a straight down methyl. That carbon 1 is a methyl group. In the back, I see going down on either side hydrogen, and carbon 4 is going straight up. So this is what we're seeing in the next Newman projection energy diagram for the conformational analysis. That's how it's derived. So when we look at this, what I want you to notice is that the staggareds do not have equal energies. Okay. And also the eclipsing conformations do not have equal energies, right? If you look, there's one that's particularly bad. And if you look at the bottom, there are two that are particularly good. Well, it could be argued that's the same one. Okay, so what about this? Well, you have varying eclipsing and staggered conformations with every 60-degree dihedral angle. So if I start with the two methyl groups opposite to one another, and I do a 60-degree click to the right, keeping the methyl in the back. Notice the methyl in the back is kept down. I'm only rotating the front carbon. Rotating the front carbon 60 degrees, they're now eclipsing. So pay attention. This conformation, the first one I started with, has the lowest energy. Why? It's staggered. And the methyl groups are as far apart from one another as possible. That's as far as they can get. So there's two things going on here. I want you to pay attention to torsional strain. That's the staggered versus eclipsed. Staggered versus eclipsed. And I want you to pay attention to something called steric hindrance. That's when you have bulky groups, like a CH3, and it comes in close proximity to another bulky group, perhaps another CH3 in this case. Here we have the lowest energy because the methyls are minimizing steric hindrance, and there's no torsional strain because they're staggered. The first eclipsing conformation that we get to, when you have something that is starting to get closer and closer to one another, then you're starting to increase the energy. So you can see that in the 16 kilojoules per mole. Also, now we do 60 degrees more, we see that we've got the two methyl groups now staggered. But why doesn't it have the same staggered energy as the first one? Well, now we're starting to see those methyl groups get super close to each other. And now we have steric hindrance, right? So whenever I draw these two, it's like two clouds bumping into each other. That is a universal sign for steric hindrance. So in the second staggered, we have steric hindrance, but, right, it's staggered. So the good news is it's staggered, but you've got steric hindrance. So that's why it's higher in energy. We had pretty much no steric hindrance and staggeredness in the first one. 60 degrees more, and we get eclipsed. We've got eclipsed again. And now we also have steric hindrance. Man, those two are right on top of each other. So that's why that one is the highest in energy. 60 degrees more, we're back to staggered. And it's the same energy as before, it's just on the other side. Still we have, it's staggered, but you've still got now steric hindrance because they're close to each other. 60 degrees more, we have eclipsed, but no steric hindrance because the methyl groups grew farther apart. And then 60 degrees further brings me right back to the start where I'm staggered with 0 steric hindrance. So you can see that we have to look at two things, both torsional strain, when the bonds are pretty much in line with one another and repel, and steric hindrance, and that pertains to the types of groups at the end. If the types of groups are big and bulky and have electron density, then they're going to be, again, in each other's way and repelling one another. You can see this a little bit more in the diagram below. We also note that there are certain names to these special staggered positions. The best staggered position that we saw for butane is called the anti-conformation. That's when you have no steric hindrance and those two large groups are positioned completely 180 degrees to one another. They're super far apart. The gauche are the other two staggered conformations when you have steric hindrance between the two groups. So when the two large groups are right next to each other but staggered, it's called a gauche conformation. And it doesn't matter which side that they're on. Anti-conformation tends to be the most stable because you've minimized the steric hindrance. I leave you with this practice problem, and there's a couple things going on here. First, you have to draw 2-methylpentane, so it's good nomenclature review. And then I want you to draw a Newman projection of 2-methylpentane, and I want you to do it by looking down the C3, C4 axis. Next, figure out which Newman projection is the lowest in energy for this molecule. So it's kind of a 3-part question. Draw the molecule, draw a Newman projection of the molecule, and then figure out which Newman projection you would prefer based on energy conformations, minimizing the energy sterics and torsional strain.